All right. We're still talking a bit about surface characterization. This is surface characterization 3, and I've thrown in a bit of OES at the end. And OES is optical emission spectroscopy. And the reason why I threw it in, other than not really knowing where else to fit it in this class, is the two techniques we're going to talk about today are actually spectroscopy techniques, and so OES kind of fit in there. Before we go a little further, take a look at this micrograph, and it may be obvious what instrument made it. And always ask this, what could make this micrograph more informative? And what do you think it is? So take a couple of minutes. You can pause if you want to try to guess, because I'll give the answer after I uncomfortably pause and get my shaggy mop head out of my face, or at least attempt to. And I'm failing miserably. All right, so if you took a couple of seconds to think about it, again, I think everyone so far has been a scanning electron micrograph. The last two lectures, I had that Mr. Clean Magic Eraser. And this is actually a rock, and it's a geological specimen. And it was made by a special flavor of electrons. And I thought I'd throw this in a little early because we've not gotten to SEM yet. But we're talking about another flavor of electrons today called Auger electrons. And these electrons are backscattered electrons. And we'll actually mention the third flavor of electrons we use, which is secondary electrons. And I always refer to them as flavors for some reason. And so backscatter electron, we'll start talking about it now because we'll talk about it later, gives you elemental contrast because of the way the electron interacts with the atom, particularly the nucleus of the atom. And so higher atomic number or higher Z number elements give you higher brightness, basically. So let me get a pointer out. This region here that's brighter is actually a higher atomic number than this region here, which is darker, so it's a lower atomic number. So it can't tell you the exact element, but it can tell you which one is higher or lower in terms of position on the periodic table. You would need to use this in conjunction with EDS to actually determine the elements. And we'll kind of explore, excuse me, we'll explore that a little bit more intimately as the semester progresses. But we will talk a little bit about X-ray generation today, and because there's some similarities with Auger electron generation that I wanted to kind of touch upon. These are going to be high-level descriptions of the three spectrographic techniques we're going to be talking about. If anyone wants to delve deeper, feel free, but we have to kind of move on to other topics. So this is a little bit higher level than maybe I would like, but I think hopefully you'll get at least the important stuff. I wanted to draw your attention, and it's actually the wrong page. I don't think there's that many pages in the book. It's actually supposed to be 425, so I put a little typo, but it's clearly what page it is. So it's from our textbook, the Brandon and Kaplan, and I really kind of like this table because it's very simple, and it thinks of things, and I actually stumbled upon it today. I think this way. It's interesting because I always think, what kind of probe are you using? So remember the activities we've done with our hands, where our probes are our eyes, what we see with our eyes, and what we feel with our fingers, that kind of thing. And this is just going through kind of a catalog of different types of characterization methods. They call it analytical chemistry, whatever. I call it characterization and the type of probe you use. And so it's pretty cool. I like the fact that they use quote-unquote white X-rays. That just means, what does that mean, actually? I think it means polychromatic. That's very interesting. Oh, it's X-ray fluorescence, of course. Haha, here I am talking to myself, literally. But anyway, I have to remember I'm actually recording a lecture sometimes. But anyway, here are the different types of characterization techniques. Most of them are spectroscopy, so chemists like to use spectrographic techniques. And the probe used and what we're actually detecting. And so it's pretty cool. So just take a little bit of time to read it. I'll not read it to you, but let's move on. So we're again in chapter 8 in the text. We're talking about XPS and AES. XPS is X-ray photoelectron spectroscopy. AES is Auger electron spectroscopy. They really do go hand in hand, primarily because Auger electron spectroscopy was discovered by observing X-ray photoelectron spectroscopy. And so early Auger was basically using an X-ray beam as the exciter of the electron. And now most systems use an electron beam, so it's more energetic than, well, it's also controllable as well, but that's another issue. Both are surface analytical techniques and both involve an ionization process. So you're knocking an electron out of the orbital of the atom or the atomic orbit. That's what I'm trying to say. There's some chaos that ensues when you have this ionized atom. Energy needs to be conserved. The atom is trying to stabilize itself. And so some chaos ensues. And the result of this chaos gives us, as material scientists and engineers, information we need to actually understand our material. And so it's actually a really kind of interesting process and beautiful process. This, I don't know, it's kind of cool. I get it from the book. And so this is, if you read the figure caption, you know, it's an electron spectrometer. Okay, so it's kind of interesting. And most electron instrumentation, whether it's an SEM or what, is actually pretty tailorable. So you can put in different probes and stuff like that. And so I have an SEM you can do transmission microscopy with and that kind of thing. So something I want to kind of point out here, this scintillator photomultiplier is detecting X-rays. This thingamabob here is, this is detecting electrons, excuse me. I think I said electrons. This one's detecting X-rays. This, you can bombard it, so you can either detect photoelectrons or Auger electrons. The electron gun will give you any flavor of electrons in addition to X-rays. This ion gun's usually used to remove layers of material and look deeper in the surface. And so you can do kind of Z scale characterization. And so I, for whatever reason, I always kind of like it. Maybe it's because this kind of looks like a trumpet. I don't know. But it's there in the book on page 430. And so I encourage you to take a look and read the surrounding text. X-ray photoelectron spectroscopy, otherwise known as XPS, was developed in the 60s. So an amazing decade, the 60s, because I think that's also the decade of the first commercially available scanning electron microscope. And so X-ray photoelectron spectroscopy, I'll actually read the text. An X-ray photon penetrates into the inner electron orbitals. You eject a photoelectron, and it has a characteristic energy level. And so it's spectroscopy is all about characteristic energies, whether it's EDS, AES, XPS. So there's always a characteristic energy. There's several tables now that tell you what energy level corresponds with what atom, and sometimes it's very discrete. Sometimes you're looking at tenths of electron volts to tell the difference between one element and another. And I don't know, I'm distracted. It's raining quite hard. It's been an odd day weather-wise here. I shouldn't actually say that in the lecture because I tend to use this for years. But anyway, photoelectron is ejected with a characteristic energy level. Again, spectroscopy, characteristic energies, and or wavelengths for that matter. The nomenclature for the energy levels in XPS is 1s, 2s, 2p, etc. And I say this in other classes. I've not said it here, and I've have bad punctuation on etc. That should have a period there. I apologize. Here, I'll move the pointer there to pretend it's a period. So you know this process was developed by a chemist. Okay, so chemists tended to use the SPDF nomenclature for energy levels. There is a distinct body of science when all these instruments were being developed and materials characterization was in its infantile stages, where people kind of looked at the Bohr shell model and adopted KLM in terms of energy levels. And we will explore that a little bit further in a little bit more detail in this lecture. So a spectroscopist, developed the analytical technique. If the feed out or the readout of your instrument is KLM, a chemist generally developed the technique if it's SPDF. And I'll give you a nickel if you can tell me what SPDF stands for, and I'll probably tell you later in this lecture because I just can't help it. XPS uses an X-ray source. The other instrumentation that we will explore, and we might explore XRF as well, but we for sure will explore XRD in this class. The other instrumentation that exploits, I guess, X-rays is X-ray diffraction. However, there are some distinct differences in the energy associated with the X-rays and the different instruments. And so for an XPS, X-ray generator target material. So there's a difference between a radiation source and a radiation generator. Radiation generator does not emit radiation when it's turned off. So in your X-ray tube in the XRD or an XPS is turned off, it's no longer emitting radiation. If you have a radioactive source like plutonium or something, that's an X-ray source. You can't turn it off. Okay, so some terminology there. We'll get a little bit more into detail of what magnesium K-alpha, aluminum K-alpha, K-beta, that kind of business is when we talk about X-ray diffractometry, and also when we talk about energy dispersive spectroscopy, or EDS. So typical energies for an XPS, XPS systems usually use a magnesium target in their generator or an aluminum target in their generator. The energy of these X-rays are as follows. So 1.2 kilo electron volts, if you want to abbreviate, divide by 1,000, so 1.2, or 1.4 kilo electron volts for aluminum. And that corresponds with these wavelengths. Okay, so shorter wavelength equals higher energy, according to, what's the law? Planck's law, I think. So 9.92 angstroms for magnesium, 8.34 for aluminum. XRD, our XRD anyway, uses a copper K alpha. I didn't label it here. I've had it on other presentations talking about resolution and that kind of thing. But XRD uses 1.54 angstrom wavelength, and that translates to a lot more energy. So 8,000 electron volts, or 8 kilo electron volts, if you will. So some differences in the X-ray sources for these two different instrumentation types. So kind of bear that in mind. So again, target material is typically magnesium or aluminum. How an X-ray generator works, here's my picture, my painstakingly drawn, and I've used it for years. It's almost kind of my joke. And so you have a filament, and it's typically a tungsten filament, actually, so you have to replace these tubes. It's thermionic emission. It emits electrons. These electrons hit a target, and the material probe interaction, material beam interactions in X-ray. And so this is my picture. I should hang it on the fridge. Only my mother would be proud of this picture. Here's a better picture. And it's from Thermo Scientific's webpage, if you care to take a look. And they have some other explanations on the generation of X-rays and that kind of thing. But it's kind of I don't know. I found this just today, actually, and it's 2020, so I've had this picture for almost a decade. I keep it because I worked really hard on it, actually. But it kind of shows you the same thing. So here, this is depicting a dual wavelength gun, basically. So you have two distinct wavelengths. Why would you need two distinct wavelengths? Why do you think that? If we go back here, we actually have two different energies, and they're not all that different, but they're just different enough. And so if you'll see on the subsequent slides what we're actually doing with the X-rays. We're knocking out electrons, basically, okay? And to knock out an electron, you need to push it out of its happy spot, which is the orbital, okay? Whether it's SPDF, whatever. And to do that, you need energy. So it has to overcome the existing energy level it's at. And we'll kind of work through a couple of scenarios here later on to hopefully make my words that are coming out of my mouth make some sense. So this is cool because this tube, so Thermo Fisher has a variable wavelength technology, and the way they did that is they have two different target materials. Silver, why are you using silver? Silver is highly conductive, and then you have a connector, an anode that connects to it. And this is the cathode. So cathode, anode, thermionic is a hot cathode technology, very similar to vacuum tubes and that kind of thing. You emit some electrons. The electrons hit the target. It's going to have one wavelength of X-rays if you've energized the magnesium side, and it'll have a different wavelength of X-rays if you've energized the aluminum side. And so what wavelength will you have? Well, here we go. You'll have almost 10 angstroms for magnesium and just over 8 angstroms for aluminum, so higher energy for that aluminum side, basically. So an X-ray generator. In XPS now, we typically denote photons with h mu, or h times frequency, and Planck's constant times the frequency of the photon. X-rays are photons. You basically come in, hit this atom with photons. This is just kind of a crude depiction of an energy level. We excite this electron up and out of the material, basically. So we get to the Fermi level, we get past the Fermi level, and we get to past the vacuum level. We actually exit the material. And this is giving you a little clue. My poorly designed animation work function. Work function, if you don't remember, is basically the amount of energy it takes to get a material. We first think about this in terms of metals, but it's the energy it takes to get the material to basically give up an electron. Okay, so this is kind of a crude drawing, but it kind of shows you the point. We're exciting the electron in some energy level. It could be any of these, okay, to a certain point where it's actually ejected. And so that's a photoelectron. We actually hit this electron with photons. It's ejected, becomes a photoelectron, kind of going off. So this ejected electron now, and I borrowed this nomenclature from the book, and I don't know why, actually, it's sub S. I would have called it K8KE, and I should take another look and understand. I actually did, and I left more confused. But anyway, nothing against the book. It's me. So the kinetic energy equation is given by this. And so this parameter, I tried to find the right variable for work function, so I labeled it work function, so it's unmistakably work function. This is frequency. I'm sorry, this is H is Planck's constant. Mu is the frequency of the photon, and you can calculate that from the information, actually. So if you know you have your aluminum target, you could go back and calculate from the wavelength, actually, the frequency, or you could calculate the frequency from energy, because energy equals Planck's constant times frequency, and it's kind of given to you in the equation, so I'm overthinking it. But anywho, the kinetic energy of this ejected electron now, specifically the ejected electron, is Planck's constant times the frequency of the photon minus this term. So this is plus the work function, and this is the binding energy. Okay, so this is the binding energy of this electron, basically. And this actually looks very similar to the work function equation. And the binding energy term is actually what's added to the work function equation. It's actually kind of neat. You might be asking yourself the question, okay, so binding energy, this is the electron binding energy, and it's basically the energy required to knock this electron out of its shell. And we just said that work function is the amount of energy it takes a material to give up its electron, right? They are different. And if you don't believe me, just trust me. No, I'll explain it hopefully as best I can. So work function is a material parameter, so it's like global. Okay, so the work function doesn't care if the electron came from here, here, or here, but binding energy does. And binding energy is the secret to XPS that tells us which orbital it came from. So the key here is the binding energy. And if you rearrange the equation now, you actually can solve for the electron binding energy. So the Planck's constant times the frequency of the light minus this term now, which is the kinetic energy of the ejected electron plus the work function, gives you the binding energy. And so that binding energy is specific to which orbital it came from, whether it's 1s, 2s, all the way, doesn't matter, 3d, could be whatever. Okay, so that's the secret. That's the, I guess, I don't know, secret cookie. And the power's going out. So I'm actually in the middle of a storm recording this, and I'll remember this forever. Glad I'm on a battery. What you can learn from XPS, you can learn binding energies, oxidation states, and elemental analysis from XPS. And if you look at how discrete binding energy is, hopefully you get an idea of how you figure out. So binding energies is a straight up calculation. Elemental analysis is it's similar to EDS in that regard. And when we talk about EDS, I'll probably bring up XPS again, just so I don't kind of glaze over this. But this is kind of a high-level explanation of these techniques. But these are three things you can learn from XPS: binding energies, oxidation states, and elemental analysis. Very important thing. I said before up here that we have this ion gun on this schematic, and that ion gun's usually used to remove material, basically. So say you have something that readily oxidizes, like aluminum, and you want to do characterization of the bulk. And if you've ever worked with microelectronics, sometimes when you solder stuff to aluminum bond pads, you have to actually etch off the oxide, or you don't get a good conductivity between your line and your aluminum electrode. So something that oxidizes pretty readily, or say you've made something out of thin films and you want to characterize layer by layer your thin film stack, an ion gun becomes very, very handy there. And so here, this may not be the best case study, and sorry you have to watch me thumb through my slides, but this is from another book. It's actually a pretty simple book. But this kind of showing the difference in spectra as they've etched down. And so here the oxide's 10.8 nanometers thick. Here it's 3.8 nanometers thick. And it gets thinner and thinner and thinner. And you see a difference in this binding energy curve. And so you're basically going from the oxide to get an idea of what the binding energy of this alloy. And so it's a oxidized aluminum silver film. So anyway, there's better examples, and I may bring them up later. Now that I'm kind of thinking about this, might not be the best. But anyway, hopefully you get the picture. You're using your ion gun to etch it away and you're starting to see the difference in your spectroscopy. So you can again do Z-scale characterization if you have an ion mill built into your unit. Other flavor now, Auger electron spectroscopy, AES. And Auger electrons, you can actually generate it in the XPS process because of what's happening. So you're knocking out an electron with the XPS process, and the atoms have to react in some way. And the way they react is generally two ways if you've actually knocked the electron out. Okay, so we're talking about situations where you're knocking electrons out, where you're ionizing them, not when you're just exciting them and de-exciting them. When you excite and de-excite and get photons, that's fluorescence. Okay, so that's a little bit different. This is more emission. Okay, so we're knocking stuff out, so we're emitting them. Auger electrons, they're generated in the XPS process. Nowadays, though, okay, so they discovered Auger electrons on an XPS unit, but now when you design an Auger, you use an electron beam because you can actually control the energy of that beam just by controlling the current, okay, the accelerating voltage, if you will. So it's a 3-electron process, okay, is what's really important to remember. It's kind of a cool process if you think about it. So we knock out an electron shell by the beam, whether it's an X-ray beam or an electron beam. Another electron falls from a higher level to take its place. What happens is an electron panics. Okay, that's how I describe it. I mean, I can read my text and say, conservation of energy causes a third electron to be ejected, the Auger electron. Or I can just say it how I understand it. An electron freaks out and says, I'm out of here, and leaves, the Auger electron. Because it's a 3-electron process, so you have to have an electron that's knocked out, an electron that comes in and takes its place, and another electron that freaks out and leaves. So the 3 little pigs, if you will. You can't detect helium or hydrogen. And here, the nomenclature for the energy level is LM, etc. Okay, I guess I could have put KLM. Don't know what I was thinking. But anyway, let's take a look at a cartoon, and then we'll work out a problem. One cartoon, I think we're actually going to look at 2 cartoons, excuse me. So here's flavors of electrons, and that's not me sticking my tongue out as a joke. It's me going, yum, because they're flavors of electrons. Gotta love them. Typically, when you hit an electron with or a material with an electron beam per se, and in some cases a high energy X-ray beam, you get 3 flavors of electrons. Well, backscattered, you only get them if you're actually using an electron beam. So let's retract my statement as my lights continue to go on and off, distracting me more than usual. You hit a material with an electron beam, you get 3 general flavors of electrons. So highest yield, secondary electrons, but they're actually not very energetic. And we'll cover this cartoon again. This is from the book. I don't remember which page, I poorly cited it. But this is Brandon and Kaplan, John Wiley and Sons. Auger electrons, which are the subject of our current discussion, which are lower yield and also kind of a low energy. And there's 2 flavors of Auger, but they're not describing which ones on this cartoon, so not the best. Now we have extremely energetic electrons, but also with a low yield, and these are backscattered electrons, like the ones used to make the image on the first slide. So 3 flavors of electrons that we get, but we're getting Auger electrons, and we will discuss the different flavors of electrons in intimate detail as the semester progresses. This is not the only time you're going to see this. Auger electron spectroscopy, and I've done my best to draw it, and this is supposed to be the incoming electron beam. Knocks this guy out. Okay, so this is the electron that gets knocked out, and it's actually a secondary electron. Here's an electron coming in and filling its shell. Okay, so this is electron number 2. And here's the electron that freaked out and said, man, I'm out of here. Psh, the Auger electron. And here's how you calculate the energy of this Auger electron. So the energy of this level minus the energy of this level minus the energy of this level. And let's work out a problem where we kind of go through this and we compare the emission of Auger electrons with that of X-rays, because it's actually a very similar process in the electron microscopy world. Hey everybody, so I'm going to kind of take a look at two processes that happen when we knock an electron out of its shell, basically. And I'm going to try to draw this as best I can, and hopefully it becomes useful to you. And so we're looking at the Auger electron process, but there's another process that also can happen when electrons knock other electrons out of material. So we have an electron fired from a gun. And I'm going to try to draw this neatly. And I've already made a mistake, but we'll just carry on. And so what I'm drawing here is I'm drawing energy levels, and I'm trying to make things a little bit more clear when I do this. And let me take a little bit of time and just tilt my screen to make it a little easier to write on. So this would be the 1s orbital. So these are orbitals kind of hybridized as energy band diagrams. And so this 1s orbital, maybe we can have a trivia question to kind of figure out what atom this may be. But this energy level is in electron volts is 4966.4, and so this is going to be let's see how high I end up getting, kind of thinking ahead, in electron volts. This is energy in electron volts, and this 1s actually corresponds with K. Okay, so the K shell is the 1s shell. It's pretty straightforward. K is the innermost shell, corresponds with our 1s orbital. Where things get a little blurred, so to speak, is when you go any higher, actually. So our next level here is going to be, let me draw the other line as well. I'm drawing this one slightly longer, not on purpose. Made a mistake, but here we can make things matchy-matchy, as the British, or I think Australians actually say. So this is the 2s. And so this is L1, okay? And this energy level is 563.7. And we have another energy level. And so this one's going to be another 2-level shell, I guess, 2p. So this is L2. And we'll draw the accompanying one here. And this is going to be 461.5. And we have another shell. We're building a big atom. A big atom. And so this is going to be L3. And this is also going to be a 2p shell. And actually, it's going to be two 2p's, right? Yes. Okay, it's going to be two 2p's. And so this is L3. And this is 455.5. And there's spectroscopy's funny business. It's very hard to differentiate between individual 2p's. The ability to differentiate between the different orbitals gets harder and harder the farther out you get from the nucleus. So there's a key difference, staggering difference between 1s and 2s, and even between 2s and this first 2p. And but it gets less and less defined. So there's actually two 2p shells here. And so maybe I should. There's actually two 2p shells there, so don't want to confuse anybody. There's kind of another gap. Okay, so we're jumping from K to L, and we said KLM, so it makes sense that this is M. And so this is M1. And M1, it's a 3 shell. Okay, so it's 3s. And I'll draw the line again over here. And this is lower, right? And I didn't really specify what this is. This is the energy it takes to knock the electron out of this shell, really. And so it makes sense. It's going to get lower as you get farther from the nucleus of the atom, right? So it's going to get lower as you go up. So energy. So the energy is lower as you go up. So you get farther away from the nucleus. Nuke. I think that's horrible spelling, but that's okay. So the M1 is a 3s shell. All of the 3p's now get kind of grouped here. Okay. But now there's kind of a subshell. So M2, 3. And so M2 is a 3p, is one 3p. And M3 is two 3p's. So M3 is 3p times 2. So let me highlight it. Okay, kind of a note to the side. Okay, so we don't want to lose track of the other p orbitals. And boom, so we draw the other line there. So it makes sense. There's another orbital now in this atom, and it's a big atom, so we're getting to the 3Ds. And I know by convention, you do 4s first, but spectroscopy maybe is unconventional. Anyway, 3D, and that's M4, 5. And let me mark this a little better. I'm sorry. So M4, 5. And so M4 is 2 3Ds. And M5, you may have guessed it, is 3D times 3. Okay, and let me write that again. I apologize. That was a little illegible. So, what did I just say? Sorry. M4 is 3D times 2. M5 is 3D times 3. Okay? And I will highlight this. Maybe I'll use a different highlighter color for funsies. All right, so now we have our energy levels, and I neglected the money side, so to speak. And let me make the marker the same size I had it before, or at least try to remember. All right, so I missed two energy levels, 34.6 and 3.7. And we have another level here, and let's use green. And it'll be shared between the two. And so if it's in the Fermi level, it's already been knocked somewhere else. And so that's 0. Okay. So these are electrons, or the energy levels for the different electrons in the different orbitals. We have the K shell, we have the L, and then we have the M, and I've made it quite messy, but this is M. Kind of squeezed it in there, snuck it in there. All right, so we have an electron now that came in, and so I'm going to use glitter, and we have our incoming electron has come in. And let me label these two sides first. So we're going to call this the Auger, or Auger. Let me go back to this one. My tablet's really angry with me. Auger. So I'm going to kind of compare this to what happens with X-ray. And the X-ray, in this case, you would get from EDS. So I'm introducing it a little bit early, but we'll cover it again. But they're kind of similar processes. They're both spectroscopy techniques. So I felt that it bore some comparison, so to speak. And we'll get back to my unicorn glitter. So we have an incoming electron. Let's just say it comes here, boom, incoming electron. And we'll make the pen a little smaller. This incoming electron now, it knocks this guy out. Wonder why it put it behind. That's interesting. This guy gets knocked out. Gets knocked out. Boom. This actually becomes a secondary electron. Secondary. Alrighty. Now we have this kind of cascade reaction that happens. And this electron, and it can be others, but this electron now decides to take its place. Okay? This electron now decides to take its place. And maybe I should highlight it a little. Okay, well, there has to be a conservation of energy. This is how I always describe it. You may disagree with the way I describe it. This electron in this level now, it can be any other level. It can be in the same band, and it can be any band between here and here. Okay, it's never in the same 2p. It's either going to, sorry, L2. Okay, it'll be a different 2p, but it's easier to differentiate L2 and L3. So it's not going to be an L2, and it can be an any energy level that's above this L2. So it can be L3, it can be M1, it can be M23 or M45. And so I'm just pretending it's coming from here. It's going to come in now, and it's going to, actually this guy fell and took its place. This guy freaked out. So the one that takes its place can be any energy level up, okay? So alpha, beta, delta, gamma. So this is going to be an M gamma, right? This one takes its place. This one freaks out and leaves, and this is an Auger electron, okay? So falls down. This guy freaks out and leaves. Just takes off. And this Auger has an energy now. And this Auger energy, let me just squeeze it in. Energy Auger is going to be equal to L2 minus M23 minus M45. And we have our energy level tabulated here. And you already know it was an incoming electron, and you can rewind it if you don't believe me. But we have our numbers now. So we have 461.5 minus 34.6 minus 3.7. So EOJ, here's my handy dandy calculator. Doo-doo-doo-doo. Gonna give you a soundtrack while I'm using my cell phone to calculate stuff again. That's always fun. 461.5 minus 34.6 minus 3.7 equals, I got 423.2. So our EOJ is 423.2 electron volts. All right. So now, drawing it a little messy, probably going to make my calculation for the X-ray further down below. But again, let's just use the same energy levels. Magic unicorn incoming electron comes in. Boom. Knocks this electron out. I'm out of here, man. This is a secondary again. Secondary electron. Again, this guy in the 3D, wants to solve everybody's problems. We now have an ionized atom. Things are unhappy. This M45 electron is going to come down, take its place. Similar scenario, but now we're talking X-rays. And so now what happens is a photon is emitted. And we tend to denote photons by Planck's constant times frequency, so a photon. And so now we have a little bit simpler calculation of what this photon energy is going to be. And this is going to be an odd one. It's going to be alpha, beta, delta, gamma. It's going to be an M gamma, which isn't very common in spectroscopy. Oh, and then I think, did I say this is probably a transition element? Titanium, maybe? So anyway, if you're interested in what atom these numbers came from, it's kind of some trivia. Maybe look it up. For fun. Okay, that's a fun. Science is fun, yes? Hopefully you guys said yes along with me. So we want to find out the energy now of this photon. And we'll do it in blue. And it's a similar process, okay? It's going to be the energy level that it came from, minus the upper energy level of the electron that took its place, right? So again, we started off, we were 461.5 minus, this level again was 3.7. And I should do it in my head, but I like using my cell phone as a calculator because it's so convenient. Oops, especially when the screen tilts, but you guys didn't see that, so you didn't need to know. Okay, 461.5 minus 3.7, so I got 457.8. EV. So two flavors of spectroscopy. One that takes advantage of the energy of an electron, one that takes advantage of the energy of a photon. This is EDS, and this would be AES, so Auger electron spectroscopy, energy dispersive spectroscopy, sometimes called EDX, my pet peeve. But EDS, energy dispersive spectroscopy. There's another flavor of spectroscopy that we use to identify elements called wavelength dispersive spectroscopy. Hopefully, by looking at the two similar, let me make it a little smaller, the two similar processes, you can see how both of these are used to identify chemical species, actually. So you can identify elemental analysis and that kind of thing. And hopefully this has kind of begun the discussion on KLM and how that fits and how that relates to SPD. I always have to do this. It's like a I don't know, idiosyncrasy I have. If you remember, S is sharp, P is principal, D is diffuse, and F is fundamental. And I always have to say that not pet peeve, I actually like it. It's an idiosyncrasy. If you've ever had me for classes before, hopefully you remember this. But anyway, you probably remember it from other people as well. Horrible highlighting. I'd never make it as a highlighter, I guess. Anyway, thank you all, and let's carry on with the lecture. All right, so we've worked out a problem. So what can you learn from AES? Discrete elemental analysis, chemical binding states, chemical composition. We may kind of come into this a little bit more. Chemical composition, chemical binding states, that all comes from the energy level of your S or KLMN kind of thing. And discrete elemental analysis, again, very similar to X-ray spectroscopy. The characteristic wavelength tells you what element is making those X-rays, or in this case, what element is ejecting the electron. Not a photoelectron, though, because it freaked out and left, basically. That's what's different about XPS and AES. And we'll talk a little bit more about the differences in the subsequent slides. Like this one, XPS and AES. So I like these kind of comparison tables. So XPS and AES, the surface is analyzed. It's a few nanometer penetration. And XPS cannot image, but if you have an electron detector, you can actually image with an AES. Okay. Photoionization process or collision process. So if you're using X-rays as your source, as were the early days of Auger electron spectroscopy, it was a photoionization process or collision process, which is what we're seeing here. Incoming beam, we also saw it on the problem we worked out with my magic unicorn beam. Incoming beam knocks an electron out, billiard ball type reaction, other people call it collision process. XPS has a big advantage, though. Even though you can't really image with an XPS, it will not charge the surface. Why? Because you're hitting the surface with photons, and photons carry no charge. With AES, particularly if you're using an electron gun, and we'll talk a lot more about electron guns before this semester is over. If you're using an electron gun, charging can occur, and we'll talk about charging in other settings as well. It will influence the results. So high-level description of XPS and AES. Let's move on to our third spectroscopy technique I said we were going to talk about today. I'm giving this lecture in the dark. I've lost power. But let us move on to optical emission spectroscopy, OES. Very interesting. If you take a look at things and this is plasma. So you strike a plasma. Plasma of different elements has different colors. And so I got this from Physics Buzz. And so hydrogen, and I have a lot of interest because I use sputter coating machines. And so I was having actually a plasma problem. And my plasma used to look purple, and it started turning white. And it basically ionizes the air. So it's an argonless system. And so I was getting the ionization of oxygen when I wanted the ionization of nitrogen. And so H2 deuterium, should have looked that up a little bit. N2O2 and mercury, so different colors. Mercury, kind of a flashlight looking thing. Different materials, different color plasmas, and if you can tell the difference now of a material by the color it is when it burns, and I think we can all agree, and hopefully we can all agree, that different materials burn with different colors. And sometimes maybe you can't distinguish it with your eye, but copper, for instance, I believe burns green. We see it in the foundry. You can actually tell now what a material is. And the intensity of the individual colors now will tell you how much of an element you have relative to another. So you can actually get some quantitative information rather than qualitative information like color. So surface chemical analysis, we can argue whether or not OES is a surface chemical analysis. You're really only zapping the surface, so I kind of call it that. But you can actually make bulk conclusions. Like it's used extensively in the steel industry. I used to work in a chem lab when I was on a 9-month co-op back in the day, where we used an OES to make sure that the steel we were using was alloyed to the correct composition. So maybe I shouldn't call it a surface chemical analysis technique. But anyway, optical emission spectroscopy, it was co-invented by Bunsen of burner fame, the Muppet, or the Bunsen burner guy. Anyway, a spark vaporizes a small portion of metal. The light emitted is then spectrosized, and the discrete spectrum lines are analyzed to determine the elemental composition. And I kind of said this before, the intensity of the spectrum lines gives relative amounts of the element. And that's actually very, very important because you can tell if it's 10% carbon versus 8% carbon and if you've alloyed properly and that kind of thing. Here's our old OES, and it was a nice instrument. It was, and I kind of have this kind of crude schematic, and you have your electrode here. You would put your specimen on top here, and then this electrode would hold it down. You'd then spark it, vaporize a very small portion, and this guy in here would have a spectrometer. And so we have a portable OES in the department, but I've not been able to take a photograph of it. And so this is our old OES. I actually miss it. It was a lot of fun. The arc source, the electrodes are typically graphite or amorphous carbon. It's a direct current power source. Just zaps it. It's kind of cool. In larger systems, and we're going to see this exact slide again, and with kind of a similar explanation, but I'm kind of repeating myself a little bit today, but that's okay. You zap your metal, you end up getting, this is really a crude representation, but you zap your metal, you get some emitted light. This emitted light hits a diffraction grating. The colors are then sent to discrete locations, so you're essentially splitting the light. And you actually have individual detectors located in a circle. And Bragg's law will tell us the wavelength. Okay, so at a given angle theta, we'll get a given wavelength. Wavelength corresponds to color, and we'll talk a lot more about that later. I'm depicting red, green, and blue, but different color, different wavelength, that means a different position. These are photodiodes. Actually, I should have called it that, but they're photodiodes. So the intensity will give a different current. So if this corresponds with copper and this corresponds with carbon, and this corresponds with sulfur, and this is much more intense than this. You know, we can say there's more copper than carbon, that kind of thing. Okay, so hopefully that is a good explanation. If you have any questions, always feel free to ask. Monochromator, so the smaller, and some of you may have seen it. We have a portable, I want to say it's an Oxford Instruments OES in our department. The light again is emitted, it hits a mirror, it then hits this grating, and this grating rotates now. And it's going, there's another detector here, a photodiode here. So I should have been a little more specific, but there's a photodiode here. And the discrete angle that generates a signal here, that corresponds. So again, we're still using Bragg's law, and we're still using an angle. But now you're not going to get a signal unless you have a characteristic angle from your rotating grating, basically. And the angle, again, tells you what color it is. The intensity of the light here tells you how much it is. And kind of repeating myself again, I don't think I need to talk about it, but I kind of said diffractor in large systems. And so this is a monochromator. And so you really only get one color at a time. So the analysis might be a little bit longer on these portable systems because you have to wait for it to move across the whole spectrum and then figure out which light had the most intensity. Whereas with a polychromator, you're seeing all the light at the same time. So a polychromator would probably give you faster analytical results. On the subject of color, human eye sees light. Could we be our own spectrometer? Kind of asking that. But color, I'm kind of saying this because it comes in two flavors. And so I'll repeat this in kind of a different context. So our eye, we see a red apple. We're taught as young children that, you know, the white light's made up of all the colors. It hits the apple. It absorbs all the other colors, and what we see is red, basically, because that's the color that wasn't absorbed, right? There's another flavor of color called structure color, and we'll talk about this a lot more. Probably the most famous example is the morpho butterfly, which is actually used by creationists and evolutionists alike to kind of field their own ideals. Very interesting, though. There is no blue pigment on this. It's all a diffraction grating, basically. So the morpho butterfly, very famous, but there's other examples of structure color in nature. And so very cool. If you want more information, I got this figure from this article, Sensors, written back in 2003. And so that about wraps it up. We talked about AES, OES, and XPS, and hopefully you've enjoyed our little segue into spectroscopy, and we'll start talking about other subjects in the next lecture. We may talk about surface characterization later, and we may bring up some of these topics as they relate to other topics in the class and talk about them in a greater detail. But thank you for your time, and hopefully the lights come back on at my home. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.